The diversity of life on Earth is astounding, from microscopic bacteria to colossal whales. Despite their differences, all living organisms share a common ancestor called LUCA. LUCA was not the first life form, but it is the one from which all existing life descends. Imagine LUCA as a single-celled organism in a hot, ancient world. This ancestor passed on its genetic information, connecting all life in a vast family tree. Early scientists grappled to understand life. Many believed in vitalism, the idea that a special force animated living things. This notion was challenged by groundbreaking experiments. In the 1780s, Antoine Lavoisier showed that respiration was a chemical reaction involving oxygen. Luigi Galvani, in the 1790s, showed that electricity could stimulate muscle contractions in frogs. These discoveries hinted that life might be governed by the same physical and chemical laws as the non-living world. Defining life is surprisingly complex. Scientists and philosophers have long debated what truly distinguishes living organisms from non-living matter. A widely accepted definition describes life as a self-sustaining system capable of Darwinian evolution. This means that living things can reproduce and pass on their traits to their offspring, with variations arising over generations. These variations are subject to natural selection, where those best suited to their environment are more likely to survive and reproduce. Several key characteristics differentiate living organisms from non-living matter. Living things exhibit a high degree of complexity, with intricate structures and processes. They engage in metabolism, a continuous exchange of energy and matter with their surroundings. Living organisms maintain boundaries, separating their internal environment from the external world, often through structures like cell membranes. Most importantly, they have the remarkable ability to reproduce, ensuring the continuation of their lineage. While non-living matter may exhibit some of these traits in isolation, only living organisms possess all of them interwoven in a complex tapestry of life. The question of how life arose from non-living matter is one of the most fundamental and enduring mysteries in science. Several compelling hypotheses attempt to explain the origin of life's building blocks, the molecules essential for life as we know it. One such hypothesis is panspermia, which suggests that these building blocks arrived on Earth from outer space. This theory is supported by the discovery of organic molecules such as amino acids in meteorites like the Murchison meteorite. Furthermore, complex molecules like isopropyl cyanide, a possible precursor to DNA, have been detected in interstellar clouds. Another prominent hypothesis is the primordial soup theory. This theory posits that life arose in a soup of organic molecules in early Earth's oceans. Volcanic activity and lightning strikes provided the energy needed to drive chemical reactions, forming these essential building blocks. The famous Miller-Urey experiment in 1953 demonstrated that amino acids, the building blocks of proteins, could form under simulated early Earth conditions. While the exact conditions of early Earth remain uncertain, the Miller-Urey experiment provided compelling evidence for the plausibility of the primordial soup theory. The leap from a primordial soup to complex life is staggering. One theory is the RNA world hypothesis. It suggests RNA was the primary genetic carrier. RNA can store genetic information and catalyze reactions. Ribozymes support this hypothesis. Protocells were crucial in life's origin. Lipids can form membranes in water. These membranes created efficient internal environments. Protocells may have led to true cells. Life's emergence was a gradual process driven by natural selection.